Aha. Terrible title, really, but we'll see why it is that way. I can't really match the pile of poo that came before me. But I did bring an animal to torment. This is a happy accident. That's a spider monkey you're looking at. And we can torture it a little bit like that. It's not a very interesting demo, but the point is we want to torture it much more quickly. So we do it on 8 cores, and that's what I'm going to talk about. Let's see if we can find the window. There we go. Okay, so Multicore. You go to the electronics store and you look at phones, and every phone has at least 2 cores. Most of them have 4. You can get a quad-core phone for $150, and that's in Norway. Laptops have 2 to 4 cores, and they're hyper-threaded. They're really powerful. Desktops, if you still have them, have at least 4 cores, and 16 is not uncommon at all. And this trend is just going to continue. Cores are not going to get much faster, but we can add more cores and we can make them communicate much more quickly for the next several years. And that is going to be how computers get faster. And for native apps that are written in C# and C++ and Swift and Java, this is just fine because they're multi-threaded already, and the multiple threads are just going to pick up the extra cores and get the extra power. JavaScript, on the other hand, is stuck on 1 core. It's always been that way. The JavaScript engines can use more than 1 core because they use cores in the background for garbage collection and compilation and so on, but by and large, when your program is running flat out, as we'll see in a little bit, it uses 1 core. That's all it gets. And obviously, if this continues, JavaScript is not going to remain a competitive programming language. And you wonder, well, okay, so there are more cores available, more power is available. What are we going to use all this power for? So here's a true story. My wife commissioned a website for a museum she was working at about 18 years ago, and that site has 3 lines of JavaScript. And those 3 lines, which are perfect for that site, selected a random image for the front page. But in 2015, Office applications are written in JavaScript. And the reason is partly that computers have gotten a lot faster, but JavaScript has gotten a lot better in that time. And I really want that to continue. I want JavaScript to keep up with 90 frames per second of VR rendering. I want it to have great AI for games. And I want people to compile C++ and Clojure and other languages to JavaScript, and for JavaScript to be the assembly language of the web. And to do that, we're going to need all the power that we can get. We need to use these extra cores. So people have tried to pick up this power previously, several attempts actually. One is known as parallel JavaScript, and came out of Intel, was known as River Trail. We put it into Firefox. We spent a lot of time trying to optimize it and implement it well. It uses this data parallel functional style. So if you have an array and you're mapping a function across the array, why don't you just map that function in parallel? You pick up multi-core performance, but JavaScript remains single-threaded, everything is safe, and everyone is happy. It's really appealing. Unfortunately, this is really hard to implement well. We could not get the performance that we wanted out of this. The functional style doesn't work real with high performance because you end up creating a lot of new arrays all the time, and it's actually pretty tricky to specify exactly what JavaScript subset that you can use in the function. So another thing that people have tried is to use workers and messages. You can spawn off web workers. Spawn off a worker, you send it a message, say, go and do this for me. It does the thing, and it sends a message back to you, says, I'm done. And for some applications, this works really well. If the worker can work in isolation, it doesn't need too much shared data, and you don't need to send too much data to it or receive results that are very large, then this is a great way of using multiple cores in JavaScript today. All the browsers support this. There's no magic in it. And you can optimize it with message channels, and you can optimize it by transferring memory instead of copying it. But unfortunately, for a lot of the use cases that we're interested in, like VR and rendering and so on, things where we are really looking for parallel computation, workers and messages don't work really well because they are in separate memories. It's costly to communicate, and it's really costly to coordinate by message passing. So I want to make a pitch for a different approach. I want to add shared memory to JavaScript in the browsers, and I want to let the workers operate on that shared memory in parallel, reading and writing the same memories and communicating through the memory. And this gives us better performance. And the reason it does that is that message passing through the memory is much, much faster than message passing through the event loop. Operating on shared data is much faster than copying it. It also gives us better program flow because we don't have to go through the event loop if we don't want to. We can just use messaging through the shared memory in the algorithm synchronously. It adapts better to the use cases. And the way it does that is that if you have, for example, a data parallel problem, like processing an image, then you can use a data parallel library on top of shared memory and get full multi-core performance for that task. But if you have a different kind of problem, like a work queue or a work list type of problem as for a search, you can use a task parallel library to structure that instead. And those libraries, the data parallel library and the task parallel library, can be bundled as prepackaged libraries that hide the communication, the synchronization, and many other problems. And so it allows JavaScript to use more cores routinely, which is difficult if you have to adapt your program to the low-level APIs all the time. So I'm going to do a little demo. Oh, let's get rid of the monkey. And this is kind of silly. This is a Mandelbrot animation. Let's see. I have lots of time here. There's the perf meter. This is running on one core. That's not really impressive, is it? You just sort of wait for it to finish. I should have brought a joke. This really is a pile of poo. But wait for it, wait for it. Ah, it's done. 3.8 frames per second. That's not great. But we can run it on 8 workers, and it's much faster. Did you see the utilization? We got about 80%. Let's run it again. Let's see, run it again. Command R. Look at the perf meter. Get about 80%, 75 maybe. 20 frames per second, so that's 5 times faster on 8 cores. It's okay. But you can do much better still. You can overlap the generation of the next image with the display of the previous image. Now you're getting about 100% utilization, and you're getting 26 frames per second. And so this is the kind of power that I want to unlock with shared memory and multiple cores in shared memory. I want the cores to be able to collaborate on the problem, and the only way that they can do that effectively is by communicating through the shared memory. I actually brought one more case just for hack value. Some of you probably don't know this, but you can now use vector processing in JavaScript. There's something called SIMD on most modern chips, which is a short vector processing that's suitable for graphics. SIMD is currently most easily available in Firefox from asm.js, so this is a program written in asm.js. And it uses the overlapping display and computation that I just showed you, and you're looking at something like that. And that's 50 frames per second. So that's 11 times faster than the original program, and it's by combining technologies like these, which are so shared memory parallelism, multiple cores, SIMD, and maybe ASM.js, that JavaScript can really shine and become a computational language for the next type of task that we want to do on the web in the browser. Let's see. Tricky. There we go. So I'm going to stress you a little bit on a Friday morning after the party. But I'm going to walk through some code. I don't expect all of you to follow me to the end. That's okay. There's going to be some new concepts and some very bizarre things going on here. But my example is a simple little program that's called PostMessage, which is a drop-in replacement for the PostMessage that we currently use in the browser for communicating between workers. It's a simple JavaScript class, and it hides most of its shared memory use, but it'll show up here and there, and we'll go all the way down. The important thing to notice here is that this is a JavaScript library. Most of the code that you're going to see is just plain JavaScript. Occasionally, the shared memory APIs will show up. But this is a bundled replacement for PostMessage that anyone can use. And if you want to write your own because you don't like mine, you can write your own. And this is what some of you will recognize as the extensible web approach. We provide some low-level, powerful, and occasionally hard-to-use primitives, and we allow them to be bundled into libraries, and then we can experiment with which libraries work in which situations and so on. And it doesn't lock us into providing high-level structures in the language directly. It allows us to be much more flexible than that. How we do that? Much better. So here's the example program. So we have two programs here. There's a main program on the left, and the first thing it does is create a worker, which is the one on the right. After it's created the worker, it creates some shared memory by allocating an object of type shared array buffer. And then it sends that to the worker using the regular post message, using the transfer syntax that some of you probably know. And the worker receives that, and after that, we're set up. That's the only kind of inter-process communication that we actually need to get things set up. And then what happens is that on both sides, see the line there that says var m equals new post message. Both of them create a new post message object on the shared memory. And then the main program sends an object. It's an object with one field item value 37, sends it to the worker. The worker receives it. That's the second red arrow. And then the worker sends OK as a string back to the main program, which receives it, and that's the third red arrow. And what's important here, like I said, is that post message is just JavaScript code, and so we're going to dig down into it and look at how it's implemented. So here's the constructor. Post message is really very straightforward. It composes two other classes, both of which are JavaScript classes too. They're not built into Firefox or anything like that. One is called IntQueue, and apparently it uses shared memory because it takes the shared array buffer argument for its own argument. See the first argument to IntQueue there. The marshaled is not very interesting. It just flattens objects. In the receive method, you see that it uses the queue to get data by calling the dequeue method, and then it unmarshals the data and then returns it. So this is all that receive looks like. If you've seen a queue before, this should be familiar to you. So we'll look at IntQueue. IntQueue does something unusual. It creates something called a shared int32 array on the shared memory. So that's a view on the shared memory, treats it as an array. And it creates two of these properties, one called meta and the other one called queue. Meta is used for metadata and queue is used for the queue data. And then it creates a data type called a synchronic. A synchronic is a shared variable that works as a simple communication channel. Shared int32 array is a new primitive type, but the synchronic is just a JavaScript class. So we'll look at that in a minute. You can see that I've left some arguments out from the constructor lists here. That's where I am hiding all the work that you have to do for your own memory management, and we'll get back to that. So here is the dequeue method of the IntQueue. The things in red circles are accesses to shared memory. The first one reads a variable from the meta array that we just created, that view that we just created in the previous slide. The line after that gets something out of the queue array. And finally, the last red blob writes something back into the meta array. And so you'll notice that shared memory accesses look exactly like unshared memory accesses. And they also cost the same as unshared memory accesses. The shared arrays are really just like normal arrays, except that the memory that they map is shared. But there's something else going on here. Shared memory has a cost, which is that if two workers access shared memory at the same time, then they have to coordinate those accesses, or the results that they get out might be meaningless. For example, if two workers write to the same cell at the same time, you have no idea what's going to end up in that cell. And so for shared data structures like this queue, you have to have a lock. And that's what these two calls do. The first call acquires the lock, and the second call releases it. The first call also waits for data to be available in the queue, and so it goes to sleep until the data is available, and it gets the lock, and then it comes back here, and then we can access the queue data as we like because the lock is held, and so it's safe to read and write meta and queue. So let's look at how that coordination is done. This is the function acquire with data available that we just looked at. It uses that synchronic variable that we allocated a little while ago called data available in the blue circle there. The way that works is that, well, let's look at the function. It tries to take the lock, and it says that if the available data in the queue is more than 0, then return, because then we have some data and we're done. We have the lock, and so we return. Otherwise, release the lock again and then wait for there to be some data. And the way that waiting is done is by saying, I want the synchronic to change its value. Expect update. Wait for it to change its value. Meanwhile, on a different worker, somebody who sends will call release with data available after they're done sending. That will increment data available in the red circle, and that sends a signal to the worker that's waiting on the update of the synchronic and wake it up again. And finally, for those who are still with me, this is the bottommost layer. This is where we implement Synchronics. And this is where we see the shared memory APIs again. There is a new object called atomics, which has a bunch of static methods on it. So for example, down at the bottom here, you see a call to atomics.add. That takes 3 arguments. It's a shared typed array, so like the shared int32 array that we looked at. It's an index into that array, and it's a value, and it adds that value into that cell of the array. Now, some of you might think that, well, we already have an operator for that. It's called plus equals. Actually, plus equals is problematic because plus equals might be divided into multiple operations. And so if a worker is updating a cell with plus equals, it might read the value. Some other worker might come in and change the value, and then the worker might write the value again, and that doesn't actually end up with the right value in the cell. And so we have these atomics that guarantee that things will happen without interruption, and they'll happen in the right order that we want them to happen. The other thing that's going on here is that we have these 2 functions, few takes wait and few takes wake. Few takes wait says, go to sleep, wait until I'm woken up. Few takes wake says, wake that thing up. And this is how expect update is implemented. It says that if the value is not on the 1, 2, 3, 4th line of expect update, you say if atomics load this is not equal to value, then break. That means that if the value has already changed, then we're done. Otherwise, we go to sleep. And then later in add, it actually wakes it up because then it has changed the value. So, to summarize what we just saw, we have PostMessage, which is a JavaScript class that emulates the PostMessage that's built into the browser, which is built on IntQueue, which is another JavaScript class that provides a queue through shared memory, which is built on Synchronic, which is a simple communications channel, but it's also a JavaScript class, which is built on several new primitives. Shared array buffer for allocating memory, shared typed array for creating views on shared memory, and the atomics for creating atomic operations and sleep and wake up. And of course, there are workers that provides threads for us, the workers we already had. You're probably curious, at least some of you probably are, I hope, how our post message holds up against the regular post message. Actually, it does really well. I have a silly benchmark that ping-pongs this object with one field item, value 37, between main and a worker a lot of times. The regular post message built into the browser, in Safari, which is much faster than all the other browsers on my computer, it gets about 80,000 messages per second. My post message going through shared memory in Firefox Nightly on the same computer gets about 360,000 messages per second. So that's nice, but the thing is, now I'm emulating post message. Why on earth would I do that? If I really wanted to communicate quickly, I could do much, much better. If all I want to do is send an integer, I have a little benchmark program that gets me 6.5 million messages per second on this computer through shared memory. And so shared memory allows us to optimize message passing in a completely different way than post message would allow us to do. Let's take another step up. What about web APIs? Web APIs, unfortunately, have to be adapted to use shared memory. The reason for that is safety. Shared memory can be updated by any worker at any time. And so a web API implementation that looks at a piece of memory and says, I know what the value of that cell is, can't actually rely on that cell not to change. And so for each web API, we have to at least consider the fact that memory might change under its feet, and we have to adapt them for that. So the obvious contenders for inclusion initially is Canvas, WebGL, and various image APIs that already use typed arrays and might process large amounts of data that fit into shared memory. For example, Canvas might look something like this. This is not official or anything like that. I'm just sort of off the top of my head. Instead of calling create image data on the Canvas context, we would call create shared image data, and it would give us a shared array buffer instead of an array buffer. We would then distribute that shared array buffer among the workers, and they could generate image data into it in parallel. And then we just use put image data on that memory like we normally would. And that would prevent us from copying. It would prevent us from sending memory back and forth between workers and the main thread. Everything would just happen through shared memory. So there's no free lunch, not even remotely. Shared memory can be really hard to use. And I'm going to go through some of the problems that we expect to see with this. So first of all, shared memory is flat arrays. There are no objects. There's no garbage collection. You want an object, you simulate the object on top of the flat memory. This is not great. You also have to do your own memory management. I mentioned this briefly earlier. You have to figure out where in a piece of shared memory your synchronics and your shared arrays and so on are going to live. And so that kind of bookkeeping is not very hard for allocation, but it's a little tricky for deallocation, because all the workers have to agree to deallocate an object at the same time. Then there are some generic problems with multi-core programming, such as locking problems, such as race conditions, deadlocks, and starvation. These are things that happen if you don't lock enough, you lock too much, or you lock at the wrong place. It's frequently hard to get your locks to do what you want, and it's hard to debug locking problems. And so this is a cost that we just get from going to multi-core. The next item, optimization, speculation, and platform dependencies, is actually much worse in some sense for the web platform, because it makes, if we adopt shared memory for the web platform again becomes machine dependent. The reason is that the JIT compiler rearranges operations. The hardware rearranges operations, and so actually two writes that you think are in one order might actually be executed in a different order. And there are platform dependencies, so x86 and ARM don't work the same way at all. By adding shared memory, we reintroduce these kinds of things into the JavaScript memory model, and it's kind of messy. And finally, workers are much more expensive than threads. We think of workers sometimes as threads, but each worker gets a separate heap, a separate global environment. It gets to compile a separate copy of the program into separate object code and so on. So hundreds of threads is usually fine, but hundreds of workers is not usually fine. So what's next? Where are we at? Shared memory is in Firefox Nightly right now. It's been there for a little while. And asm.js supports shared memory, and it has a drop-in replacement for pthreads, so you can compile multi-threaded C++ programs and run them on the web platform. Shared memory, though, will not ride the Firefox release trains until it's been standardized. So we're talking to TC39, ECMA, about standardizing this, and probably the API will change a little bit in that process, but the fundamentals should be what we've seen here. And finally, Google has announced that they are going to start implementing at least shared array buffer. We have had a good relationship with Google through the design process, and we're really happy that they're picking it up. So I leave you with some resources. The first link there has links to specification and examples and demos and what have you, and the slides here will appear there eventually. And that's what I have So thank you.
Thank you, Lars. There are a few questions for you, so if you want to join me here.
Veldig raskt.
I think you might have lost a few people, and I think those of us that you did lose are very grateful that there are people like you working on this for us, understanding it all and making it better. Some of the questions, so there's quite a few questions in the stream here. I guess one of the questions is how far behind is JavaScript currently with this in relation to other parallel languages?
It depends a little bit on what the question exactly means. I mean, there are two meanings to that question. The one is how quickly do we have to move to catch up with other languages? And you know, JavaScript has been doing well on single core for a while, and so we just have to get this right. But the other meaning of the question is this facility comparable to what other languages have? And I don't think it is. This is actually very low level. I think this is the first step. Like I said, there are no objects, no garbage collection. If you look to the future, you probably want to take something like typed objects, which is a new idea for ECMAScript 7, and map them on to shared memory, so at least you have structures of named fields that you can manipulate in shared memory, and you don't have to simulate all your own objects.
Yeah.
So we want to build libraries. I've started building some libraries on top of this for data parallel computation and so on, and it's very promising because they're easy to use and they give us good performance. You saw on the Mandelbrot benchmark, which uses such a data parallel API or library, that the performance is there. But there's a ways to go because other languages have sophisticated libraries built already.
So do you think JS could run and compete on supercomputers, sort of in the future against things like MPI and OpenMP?
I think JavaScript is probably not moving into that niche, partly because it's an untyped programming language.
Yeah.
It's not a natural fit for it.
But where do you see this going then? I mean, is it getting ready to do really heavy lifting?
I think that for so I have this favorite example. There's a language called Halide out of MIT, used for image processing, and it's a domain-specific language, and they generate code for whatever platform they're running on. And they make the argument that you want to, depending on the kind of processing that you do and the kind of image that you're processing, you want to specialize either for SIMD or for multicore or for GPU. And that's the kind of thing that I see this fitting into, is really, it is being used for rendering and heavy image processing, but in concert with SIMD and GPU. And we have to find out what the strengths of multicore are and find out how it fits into that ecosystem and how that can be used while we're also using the other things that JavaScript has to have available.
Yeah. There's a question here about how does the shared memory post message compared with the data transfer post message?
Can you repeat that, please?
Yeah, so how does the shared memory post message compare with the data transfer post message?
Oh, yeah, I see.
Yeah.
Well, it depends on what it compares with, but basically they do the same thing, more or less. They marshal data into a flat structure and then move it over, except that mine is written in JavaScript and the other one's written in C++. So they're comparable. Yeah.
How stable is this? How far from being ready for prime? So the question here is about the interlocking problem. Is that a hard problem to be solved? Or how hard is it proving to be?
Well, it's pretty stable. We use it for a lot of testing right now internally.
Yeah.
Haven't made any announcements, I think, that are monumental, but it feels reliable. It's a simple API, and it's not hard to implement it. And so there are limited things that could go wrong. It's hard to use it, though. So that's the cost. Yeah.
Yeah. One final question. With the shared memory, could you compile Rust to JS and then get the advantages of the borrow checker and multicore code?
Could I Compile what to JS?
Rust.
Oh, I see. Well, in principle, there wouldn't really be any issue with that. Like I said, C++, Clojure, Rust, why not? Yeah.
Anything, really?
Yeah. I mean, the thing is that with ASM.js, which is the low-level execution model, and this shared memory stuff, which is the low-level memory model, there really isn't a limit. So unless the language requires its own garbage collection and so on, when it becomes difficult, right?
Yeah.
Yeah.
Wow. I'm really happy that we have people like you working on things like this, because that was really interesting to see. Thank you, Lars.
Thank you.